Something absolutely bizarre happened in the early universe, and we're only now beginning to understand just how strange it really was. Imagine looking back in time, peering into an era when the cosmos was barely a tenth of its current age, expecting to see primitive, chaotic clouds of gas slowly coalescing into the first galaxies. Instead, we find monsters. Red, dust-choked behemoths that shouldn't exist, building stars at a pace that makes modern galaxies look lazy, and challenging everything we thought we knew about how the universe evolved. These are the red monsters, and their existence is forcing physicists to reconsider fundamental assumptions about cosmic evolution, dark matter, and the very process by which structure emerged from the primordial soup of the early universe. Their discovery is not just another interesting astronomical observation, it's a direct challenge to our entire timeline of cosmic history. Let's start with what makes these objects so profoundly weird. When the James Webb Space Telescope turned its infrared eyes toward the distant universe, astronomers expected to see small, irregular proto-galaxies, the building blocks that would eventually merge and grow into the massive spiral and elliptical galaxies we see today. The standard model of galaxy formation suggests a bottom-up approach: small structures form first, then gradually combine through mergers and accretion over billions of years. By this logic, massive galaxies like our Milky Way should only exist in the mature universe, billions of years after the Big Bang. But that's not what Webb found. Instead, lurking in the cosmic dawn, less than a billion years after the universe began, there they were, 3 galaxies with masses comparable to our own Milky Way. To put this in perspective, these galaxies achieved in less than a billion years what should have taken 4 or 5 times longer. It's like finding a fully grown oak tree sprouting from soil that was bare ground yesterday. The implications ripple outward in every direction. If galaxies could grow this massive this quickly, then either our models of how gas collapses and forms stars are fundamentally wrong, or something very different was happening in the early universe that we haven't accounted for. Perhaps dark matter behaved differently when the universe was younger and denser. Perhaps the initial density fluctuations that seeded galaxy formation were much more extreme than we thought. Or perhaps there were mechanisms for rapid mass assembly that simply don't operate in the modern cosmos. But their mass is only the beginning of the mystery. These galaxies earned their nickname, red monsters, because of their distinctive spectral signatures. When we look at distant galaxies, we're essentially conducting astronomy through a time machine, seeing them as they were billions of years ago. The light from these objects has been stretched by the expansion of the universe, shifting it toward redder wavelengths in a process called cosmological redshift. But these particular galaxies are red for an additional reason: dust. Dust in space isn't like the dust under your bed. Cosmic dust consists of tiny particles, often containing silicon, carbon, and various metals, that form in the atmospheres of dying stars and are scattered into the interstellar medium. This dust absorbs bluer light and allows redder wavelengths to pass through, giving dusty galaxies a characteristic reddish appearance. The presence of substantial dust tells us something crucial: these galaxies had already gone through multiple generations of stellar evolution. Stars had been born, lived their lives, and died, creating and dispersing the heavy elements that make up dust. This cycle normally takes considerable time. Finding dusty galaxies in the early universe is like discovering sophisticated pottery in an archaeological dig that should only contain stone tools. It suggests an accelerated timeline of chemical evolution, with stars forming, dying, and enriching their environments with heavy elements at a pace that seems impossibly rapid by our current understanding. Even more intriguing is the rate at which these red monsters were forming new stars. Star formation efficiency is a measure of how effectively a galaxy converts its gas into stars. In the modern universe, this process is relatively slow and inefficient. Galaxies like the Milky Way convert only a small percentage of their gas into stars in any given period. Various factors limit this efficiency: turbulence in the gas, stellar winds from existing stars, and explosive supernovae all work to heat and disperse the gas, making it harder for gravity to compress it into new stars. But the red monsters were forming stars at roughly twice the efficiency of galaxies in later epochs. They were stellar factories operating at maximum capacity, churning out new stars from their gas reserves with remarkable effectiveness. This suggests that the conditions in the early universe were fundamentally different from what we see today. Perhaps the gas was denser and easier to collapse. Perhaps there was less feedback from existing stars to disrupt star formation. Perhaps the initial collapse of dark matter halos in the early universe created conditions uniquely favorable for rapid star birth. This brings us to one of the deepest questions in cosmology: how did structure form in the universe at all? In the immediate aftermath of the Big Bang, the universe was remarkably smooth and uniform. The cosmic microwave background, the afterglow of the Big Bang that we can still detect today, shows temperature variations of only about 1 part in 100,000. Yet today we live in a universe filled with structure, galaxies, clusters of galaxies, and vast filaments of matter separated by enormous voids. The bridge between these two states is dark matter. While we cannot see dark matter directly, we can infer its presence from its gravitational effects. Dark matter doesn't interact with light or normal matter except through gravity, but that gravitational interaction is powerful enough to shape the entire large-scale structure of the universe. In the early universe, even tiny density fluctuations in the dark matter distribution would have been amplified by gravity. Regions that were slightly denser than average would attract more matter, becoming denser still, in a runaway process that eventually created the cosmic web we see today. Normal matter, the stuff that makes up stars, planets, and us, fell into the gravitational wells created by dark matter. As it fell, it heated up and eventually began forming the first stars and galaxies. This process should have been gradual, with small objects forming first and larger structures assembling over time through mergers and continued accretion. The red monsters suggest that this neat picture is incomplete. Perhaps the initial density fluctuations were more varied than we thought, with some regions being significantly denser than the average, allowing them to collapse and form massive galaxies much earlier. Perhaps the interplay between dark matter and normal matter in the early universe created conditions that could rapidly assemble enormous quantities of mass. Or perhaps we're missing something fundamental about how dark matter behaves under extreme conditions. Consider the challenge of moving mass around in the early universe. Gas can flow relatively easily toward regions of gravitational attraction, but this process has limits. As gas falls into a dark matter halo, it releases gravitational potential energy, which heats it up. This creates pressure that resists further collapse. Additionally, once stars begin forming, they inject energy back into the surrounding gas through stellar winds and supernova explosions, heating it and pushing it away. These processes should limit how quickly a galaxy can accumulate mass and form stars. Yet somehow the red monsters overcame these limitations. They accumulated Milky Way scale masses while the universe was still in its infancy, and they did so while maintaining prodigious rates of star formation. This suggests that either the early universe provided conditions that minimized the usual impediments to rapid growth, or these particular galaxies were fortunate enough to form in regions where everything conspired to enable exceptional mass assembly. One possibility is that these galaxies formed at the nodes of the cosmic web, where multiple filaments of dark matter intersected. At these intersections, gas would flow in from multiple directions, providing a continuous supply of fuel for star formation. The rapid inflow would maintain high densities, enabling efficient star formation despite the usual feedback mechanisms. Think of it like building a fire. If you can continuously add fuel faster than the existing flames can consume it, you can build a much larger fire much more quickly. Another intriguing possibility relates to the nature of dark matter itself. Most cosmological models treat dark matter as cold, meaning it moved slowly in the early universe and could clump together on small scales. But some alternative theories propose different types of dark matter that might behave differently under early universe conditions. If dark matter was somewhat warmer, or had some small self-interaction, it might have created different initial conditions that enabled more rapid galaxy assembly in some regions while suppressing it in others. The discovery of the red monsters also raises questions about what else might be hiding in the early universe. If 3 such massive galaxies exist in the relatively small patch of sky that Webb has observed in detail, how many more are out there? Is this the tip of an iceberg, with numerous other unexpectedly massive early galaxies waiting to be discovered? Or are these genuinely exceptional objects, statistical flukes that push the boundaries of what's possible within our current cosmological framework? This question matters because it affects our understanding of cosmic variance, the idea that different regions of the universe might have experienced somewhat different evolutionary paths. If massive galaxies like the red monsters are common in the early universe, it suggests that our models systematically underestimate how quickly structure could form. If they're rare, it might indicate that we've been unlucky in our observations, or that these objects required special circumstances that only occurred in a few locations. There's also the question of what happened to these galaxies afterward. Did they continue growing through mergers, eventually becoming the giant elliptical galaxies we see in the centers of galaxy clusters today? Or did something interrupt their growth, perhaps encounters with other massive galaxies that disrupted their structure or exhausted their gas supplies? Following the evolutionary paths of these early behemoths forward through time could provide crucial clues about how the modern universe came to look the way it does. The role of dust in these systems deserves deeper consideration. Dust formation requires heavy elements, which are only created inside stars through nuclear fusion. The most massive stars live fast and die young, ending their lives in supernova explosions that scatter newly forged elements into space. This material then condenses into dust grains in the cooling ejecta. The process can happen relatively quickly on cosmic timescales, with the most massive stars living only a few million years, but it still requires time. The abundance of dust in the red monsters implies that they went through an initial burst of star formation early enough to produce multiple generations of massive stars before the epoch in which we observe them. This further compounds the timeline problem. Not only did these galaxies accumulate massive amounts of matter quickly, but they also processed that matter through stellar cycles fast enough to create substantial dust. It's cosmic evolution in fast forward. Dust also plays a crucial role in star formation itself. While we often think of dust as simply obscuring our view of distant objects, which it certainly does, it also serves vital functions in the chemistry of star-forming gas. Dust grains provide surfaces where molecules can form, and they help cool gas clouds by radiating away energy. Both of these effects make it easier for gas to collapse and form new stars. In this sense, The dust in the red monsters might be part of a positive feedback loop. Early star formation creates dust, which enables more efficient subsequent star formation, which creates more dust, and so on. This raises an interesting possibility. Perhaps the reason these galaxies were able to form stars so efficiently is precisely because they built up dust so quickly. Their initial burst of star formation created conditions that made subsequent star formation easier, allowing them to convert their gas into stars at rates that wouldn't be possible in a dust-poor environment. If this is correct, it suggests that the early universe might have contained a diversity of evolutionary pathways, with some galaxies like the red monsters entering a fast-track mode of evolution while others followed more leisurely timelines. The observations of these galaxies also illuminate the power of infrared astronomy. Before the James Webb Space Telescope, finding objects like the red monsters would have been extremely difficult. Their high dust content means they emit relatively little ultraviolet and visible light, making them faint or even invisible to optical telescopes. But dust absorbs high-energy light and re-radiates it at longer, infrared wavelengths. Webb's infrared vision allowed it to see through the dust and detect the enormous stellar populations hidden within. This highlights a broader truth about astronomy. The universe is full of things we cannot see at visible wavelengths, and every time we develop new ways to observe the cosmos, we discover phenomena we never expected. Radio astronomy revealed pulsars and quasars. X-ray astronomy unveiled a violent, high-energy universe of black holes and neutron stars. Infrared astronomy is now showing us the hidden face of the early universe, revealing a cosmic dawn that was perhaps more complex and dramatic than we imagined. The red monsters also intersect with questions about the first generation of stars, known as population 3 stars. These hypothetical objects would have formed from primordial gas containing only hydrogen, helium, and trace amounts of lithium, the elements created in the Big Bang itself. Without any heavy elements, this gas would have had difficulty cooling and fragmenting, potentially leading to the formation of extremely massive stars, perhaps hundreds of times the mass of the Sun. These first stars would have been brilliant and short-lived, ending their lives in powerful supernovae that enriched the surrounding gas with heavy elements for the first time. The material ejected by population 3 supernovae would have provided the seed metals necessary for subsequent star formation to proceed more easily. Could the red monsters have benefited from particularly efficient enrichment by population 3 stars, giving them a head start on dust production and star formation? This scenario remains speculative, as we have yet to directly observe a population 3 star. These objects would have been extremely luminous but also extremely rare and short-lived, making them challenging targets for detection even with our most powerful telescopes. However, their influence might be written into the chemical compositions of later generations of stars, including those in the red monsters. Detailed spectroscopic observations of these distant galaxies might reveal clues about the nature of the first stellar populations. Another piece of the puzzle involves the role of supermassive black holes. Nearly all massive galaxies in the modern universe harbor supermassive black holes at their centers, with masses ranging from millions to billions of times that of the Sun. The relationship between these black holes and their host galaxies is remarkably tight. The mass of the central black hole is closely correlated with properties of the galaxy's central bulge, suggesting that black holes and galaxies somehow co-evolve. But this relationship presents its own mystery in the early universe. We've discovered quasars, galaxies with actively feeding supermassive black holes, at remarkably early times, less than 1 billion years after the Big Bang. These early quasars are powered by black holes containing billions of solar masses, which raises the question, how did these black holes grow so large so quickly? Normal black hole growth through accretion of gas is limited by radiation pressure from the infalling material, which should prevent extremely rapid growth. Do the red monsters also harbor supermassive black holes? If so, how massive are they, and how do they compare to the scaling relationships we observe in the modern universe? Active black holes can have profound effects on their host galaxies, injecting enormous amounts of energy into the surrounding gas through jets and winds. This AGN feedback can shut down star formation by heating and expelling the gas needed to form new stars. Perhaps the red monsters represent galaxies that formed massive stellar populations before significant AGN feedback developed, allowing them to form stars at maximum efficiency before their central black holes grew powerful enough to interrupt the process. The discovery of these galaxies also has implications for our understanding of cosmic reionization, one of the major phase transitions in cosmic history. In the first few 100,000 years after the Big Bang, the universe was so hot and dense that matter existed as a plasma, with electrons stripped away from atomic nuclei. As the universe expanded and cooled, electrons and nuclei combined to form neutral atoms, mostly hydrogen and helium. This recombination made the universe transparent to light for the first time, allowing photons to travel freely through space. This is why we can see the cosmic microwave background. It represents the moment when the universe became transparent. But this neutral state didn't last forever. Eventually, the first stars and galaxies began emitting ultraviolet light energetic enough to ionize hydrogen, stripping electrons away from atoms once again. Over several 100 million years, the universe transitioned from mostly neutral to mostly ionized, a process called reionization. This process was patchy and inhomogeneous, with bubbles of ionized gas growing around the first galaxies and eventually merging into a fully ionized universe. The red monsters, with their intense star formation rates, would have been copious producers of ionizing photons. They likely created large bubbles of ionized gas around themselves, contributing significantly to the reionization process. Understanding the abundance and properties of galaxies like the red monsters helps us model how reionization proceeded and what types of sources were most important in transforming the universe from neutral to ionized. There's also a connection to the cosmic star formation history, the timeline of how the overall rate of star formation in the universe has changed over time. Observations have shown that the cosmic star formation rate peaked several billion years after the Big Bang and has been declining ever since. The early universe was building up its inventory of stars, while the modern universe is slowly running out of the gas needed to make new ones. The red monsters complicate this picture by suggesting that the early universe might have had more vigorous star formation than we thought. If massive galaxies could form stars extremely efficiently in the first billion years, it might mean that a larger fraction of the universe's stellar mass was assembled earlier than our models suggest. This could affect our estimates of how many heavy elements had been produced at different epochs, which in turn affects our understanding of everything from the formation of planets to the evolution of life-supporting environments. Let's consider the theoretical challenges these objects present to our models of galaxy formation. Computer simulations of galaxy formation start with the known properties of dark matter and normal matter, plus the initial conditions set by the cosmic microwave background, and evolve forward in time using the laws of physics. These simulations have become increasingly sophisticated, incorporating detailed physics of gas cooling, star formation, stellar feedback, black hole growth, and more. Yet even the most advanced simulations have struggled to produce galaxies quite like the red monsters in the quantities we observe. Some simulations can produce individual massive galaxies at early times, but typically as rare outliers rather than the apparently significant population that observations suggest. This discrepancy between theory and observation is precisely what makes the red monsters so exciting. They're telling us that our simulations are missing something important. One possibility is that the simulations don't fully capture the physics of star formation in the early universe. Star formation is one of the most complex processes in astrophysics, involving interactions between gravity, turbulence, magnetic fields, radiation, and chemistry across enormous ranges of spatial scales. Even in modern simulations, star formation is typically represented using simplified, subgrid models because we cannot resolve the actual physical scales on which individual stars form. If these models don't accurately represent conditions in the early universe, they might systematically underestimate how efficiently early galaxies could form stars. Another possibility is that the initial conditions fed into the simulations aren't quite right. The simulations start with the density fluctuations observed in the cosmic microwave background and evolve them forward using known physics. But what if there were additional fluctuations on smaller scales that don't leave an imprint in the microwave background but could affect galaxy formation? Or what if the standard cosmological model itself needs adjustment in subtle ways that become important under the extreme conditions of the early universe? These questions touch on some of the deepest mysteries in cosmology. Despite its remarkable success in explaining a vast range of observations, the standard cosmological model, often called lambda-CDM for its inclusion of dark energy represented by the cosmological constant lambda and cold dark matter, still leaves many questions unanswered. What is dark matter? What is dark energy? Why does the universe have the initial conditions it does? The red monsters might be providing us with new clues about these fundamental questions. There's also a methodological question about how we measure the masses and properties of these distant galaxies. When we observe a galaxy billions of light-years away, we're collecting a tiny number of photons that have traveled across most of the observable universe to reach us. From these photons, we must infer the galaxy's mass, star formation rate, dust content, and other properties. This requires making assumptions and using models that might not be fully accurate, especially for objects as unusual as the red monsters. For example, estimating a galaxy's mass often involves assumptions about the relationship between light and mass, essentially assuming that we know how much starlight a given mass of stars should produce. But this relationship depends on the ages and types of stars present, which can vary. If the red monsters have unusual stellar populations compared to modern galaxies, our standard mass estimates might be systematically wrong. Perhaps they're not quite as massive as they appear, or perhaps they're even more massive than we think. Similarly, measuring star formation rates typically relies on observing emission from young, massive stars or from gas heated by those stars. But these measurements can be complicated by dust, which absorbs the light we're trying to observe and re-emits it at longer wavelengths. If the dust distribution in the red monsters is unusual, it might affect our measurements in ways we haven't fully accounted for. Disentangling these effects requires careful analysis and, ideally, observations at multiple wavelengths to build up a complete picture. Despite these uncertainties, the fundamental result remains robust. The red monsters are exceptionally massive and were forming stars very efficiently at a time when the universe was less than 1 billion years old. Even if some details of our interpretation change as we obtain better data and refine our models, these galaxies are telling us something important about the early universe. Looking forward, there are numerous avenues for future research on these enigmatic objects. More detailed spectroscopic observations could reveal the chemical compositions of their stars, providing clues about the generations of star formation that preceded what we observe. Observations at longer wavelengths could map the dust distribution and temperature, helping us understand the physical conditions in these galaxies. Higher resolution imaging might reveal their internal structures, showing whether they resemble modern galaxies or have distinct morphologies. There's also the exciting possibility of discovering even more extreme examples. The red monsters are impressive, but are they the most massive galaxies the early universe could produce? Or might there be even larger, more extreme objects waiting to be discovered? Webb is still in its early years of operation, with many years of observations ahead. As it surveys larger areas of the sky and observes more distant epochs, we'll build up a more complete census of early galaxies and learn whether the red monsters are exceptional outliers or representatives of a significant population. Future telescopes will continue this work. Ground-based observatories like the extremely large telescope, currently under construction in Chile, will be able to obtain even more detailed observations of distant galaxies, studying individual regions within them and tracking how their properties change across their disks. Space missions being planned for the 2030s and beyond will extend Webb's infrared vision and add new capabilities, potentially allowing us to peer even further back in time and observe the universe at even younger ages. The red monsters also connect to broader questions about our place in the cosmos. The Milky Way, our home galaxy, is itself a massive spiral galaxy containing hundreds of billions of stars. It likely formed through a complex history of mergers and accretion over billions of years, gradually assembling the mass and structure we observe today. But could the Milky Way have had a different history? Might there have been a version of cosmic history in which our galaxy's predecessors underwent rapid early assembly, becoming a red monster themselves? The answer probably depends on the environment in which our galaxy's progenitors formed. The Milky Way is part of the Local Group, a relatively small collection of galaxies including Andromeda and several dozen smaller systems. This is a fairly typical environment, neither particularly dense nor particularly isolated. The red monsters likely formed in denser-than-average regions where more raw material was available for rapid galaxy assembly. Had our region of the universe been denser, the Milky Way's history might have been very different, perhaps resembling that of the red monsters rather than the more gradual evolution we infer from our galaxy's current properties. This highlights one of the beautiful aspects of astronomy. By observing distant galaxies, we're not just learning about those particular objects, we're sampling the range of possible evolutionary paths that galaxies can take. Each galaxy is an experiment run by the universe, testing what happens under a particular set of initial conditions and environmental influences. By studying many galaxies at different distances and therefore different epochs, we're effectively watching these experiments unfold, learning what outcomes are possible and what factors determine which path a galaxy follows. The existence of the red monsters also reminds us that the universe is capable of surprises. For decades, astronomers have refined their understanding of galaxy formation, building increasingly sophisticated models that successfully explain many observed properties of galaxies in the modern universe. These models represented a genuine triumph of physical understanding, correctly predicting relationships between galaxy properties and explaining the large-scale distribution of galaxies across the cosmos. Yet nature is under no obligation to conform to our expectations, and the universe has shown time and again that it contains phenomena we didn't anticipate. Pulsars, gamma-ray bursts, dark energy, exoplanets around other stars, gravitational waves, all of these were discovered unexpectedly, challenging astronomers to expand their theoretical frameworks. The red monsters joined this tradition, revealing that the early universe was capable of producing structures that push or exceed the boundaries of what our models predict. This is how science progresses. Observations challenge theory, theorists refine their models to account for new data, and these refined models make new predictions that can be tested with future observations. The red monsters represent precisely this kind of productive tension between observation and theory, spurring deeper investigation and ultimately leading to a more complete understanding of cosmic evolution. Beyond their scientific significance, the red monsters capture something profound about the nature of cosmic time. When we look at these galaxies, we're seeing light that left them nearly 13 billion years ago, when the universe was young and the Milky Way did not yet exist. The stars shining in those galaxies have long since died, and the galaxies themselves have likely merged with others and evolved into very different objects. We're witnessing a moment frozen in time, a snapshot of an epoch when the universe was fundamentally different from what we see around us today. This temporal distance also means that we're seeing these galaxies in their youth, observing processes that might be very different from how galaxies evolve in the modern era. The early universe was denser, hotter, and richer in the primordial gas needed to form stars. The cosmic web was still taking shape, with matter streaming along filaments toward regions that would become galaxy clusters. In this environment, growth could happen rapidly, and objects like the red monsters could assemble masses in hundreds of millions of years that would take billions of years to accumulate in later epochs. There's also something aesthetically powerful about the image of these dusty, reddened galaxies churning out stars in the cosmic dawn. They represent a phase of cosmic history when structure was crystallizing out of the primordial chaos, when the first complex systems were emerging from the relative simplicity of the early universe. They are factories of creation, taking formless gas and forging it into stars, planets, and potentially the raw materials for life itself. We don't yet know if galaxies like the red monsters hosted planets, or if any of those planets might have been suitable for life. The early universe was chemically different from today, with fewer heavy elements available to build rocky planets. But the intense star formation in these galaxies would have rapidly enriched their gas with heavy elements, potentially creating conditions suitable for planet formation relatively early in cosmic history. It's an intriguing, if speculative, thought. Might there have been worlds orbiting stars in the red monsters, perhaps long vanished now, that experienced a universe very different from the one we inhabit? These questions connect astronomy to broader philosophical inquiries about time, change, and existence. The universe has a history, and different epochs of that history offer different possibilities and constraints. The red monsters existed in an era when certain modes of rapid growth were possible that cannot occur in the modern universe. Just as Earth's history includes periods like the Cambrian explosion when new forms of life rapidly diversified under conditions that no longer exist, cosmic history includes epochs like the era of the red monsters when galaxies could undergo transformations that are no longer possible today. Understanding this cosmic history enriches our perspective on our own existence. We live in a particular epoch of a universe with its own unique characteristics. The processes that formed the Sun and Earth, that allowed life to emerge and evolve, depended on the conditions present in our region of the galaxy 5 billion years ago. Those conditions were themselves the product of billions of years of prior cosmic evolution, including perhaps the early epoch when galaxies like the red monsters were transforming primordial gas into stars and heavy elements. In this sense, we are connected across time to these distant objects. The atoms in our bodies were forged in stars, some of which might have belonged to galaxies not unlike the red monsters. The oxygen we breathe, the carbon in our cells, the iron in our blood, all were created through nuclear fusion in stellar cores and scattered into space by stellar winds and supernova explosions. Some of those processes occurred in the early universe, in galaxies forming stars at prodigious rates, contributing to the gradual chemical enrichment that eventually made planets and life possible. The story of the red monsters is still being written. Every new observation adds detail to our picture of these extraordinary objects, and each detail raises new questions. Were they common or rare? How did they affect their surroundings? What became of them in the billions of years since the epoch we observe? How do they fit into the broader picture of cosmic evolution? These questions will occupy astronomers for years to come, driving new observations and theoretical work. The James Webb Space Telescope continues to observe the distant universe, gathering data that will help answer these questions. Other observatories, both ground-based and space-based, contribute complementary observations at different wavelengths. Theorists refine their simulations, incorporating new physics and testing different scenarios to see what can explain the red monster's properties. This process of discovery and understanding is one of humanity's most remarkable collective achievements. Thousands of people across the world contribute to this endeavor: engineers designing and building telescopes, astronomers planning observations and analyzing data, theorists developing models and running simulations, all working together to understand the cosmos. The discovery and study of the red monsters represents this collaborative scientific enterprise at its best, combining cutting-edge technology with sophisticated theory to address profound questions about the nature and history of the universe. As we continue to explore the early universe, we can expect more surprises. The red monsters have shown us that the cosmos is capable of producing structures more quickly and efficiently than we anticipated. What else might be hiding in the distant universe, waiting to be discovered? Perhaps there are other types of extreme objects, representing evolutionary pathways we haven't yet imagined. Perhaps there are clues to even more fundamental questions, like the nature of dark matter and dark energy, encoded in the properties of early galaxies. The universe is a vast laboratory, and we are privileged to be able to study it. Every photon that reaches our telescopes carries information about its source, about the space it traveled through, about the history of the cosmos. By collecting and analyzing these photons, we piece together the story of how the universe evolved from a hot, dense, nearly uniform state into the rich tapestry of structure we see today. Objects like the red monsters are crucial chapters in that story, revealing aspects of cosmic history that we might otherwise have missed. In the end, the red monsters remind us that the universe is both knowable and surprising. Through careful observation and thoughtful analysis, we can understand distant objects that existed billions of years before Earth formed. We can measure their masses, track their star formation, and infer their compositions. We can place them in the context of cosmic evolution and understand their role in the larger story of how structure formed in the universe. Yet at the same time, nature continues to surprise us, producing phenomena that challenge our models and force us to think more deeply about how the cosmos works. This balance between understanding and mystery is what makes astronomy so compelling. We know enough to ask meaningful questions and interpret what we observe, but not so much that everything is predictable or obvious. The red monsters appeared in our data as anomalies, objects that didn't quite fit our expectations, and that discrepancy sparked a flurry of research aimed at understanding them. Through this process, our understanding deepens, our models improve, and we gain new insights into the nature of cosmic evolution. As you look up at the night sky, remember that you're seeing light from countless stars and galaxies, each with its own story. Some of those galaxies might resemble the red monsters, massive systems forming stars at extraordinary rates, though they existed so long ago that their light has not yet reached us. Others might be more like our Milky Way, taking a slower, more gradual path toward their current state. The universe contains multitudes, and every new observation adds to our understanding of the range of possibilities that nature can realize. The journey of discovery continues, driven by human curiosity and the desire to understand our cosmic origins and context. The red monsters have opened a new window into the early universe, revealing a more dynamic and dramatic cosmic dawn than we previously envisioned. As technology advances and our observations become ever more detailed and comprehensive, we will continue to refine our understanding of these remarkable objects and the universe they inhabited. Each answer raises new questions, propelling the scientific endeavor forward, always seeking deeper understanding of the cosmos and our place within it.